Okay, so in this video we're going to be looking at a small version of differentiation table and just working through a few examples. Okay, let's start off with y equals sine of 2x. We want to be able to differentiate this. We want to be able to find the first derivative or the gradient function. So I want to be able to find dy dx. So if we look across at our table, we're looking for something that resembles sine of 2x, and if we look down here we see sine of ax. In this case a is just some constant, 2 for our example. So if we read across we can get the solution. So the solution is a cos ax, and my a, my example here is going to be 2. So we're going to have 2 cos 2x, just from using this sort of cut down version of a differentiation table. Let's try another example. Let's have y equals, what shall we say, e to the 5x. So I want to be able to differentiate that, so I want to be able to find dy dx. So again, I read down my table until I see something similar to my function, and I see e to the ax. If I differentiate e to the ax, I have a e to the ax. So in my example, a would be a 5. So if I read across, I replace all the a's with 5. So we have 5 e to the 5x. Okay, let's do one more example. In this case, perhaps we'll use what's called the linearity rules. What that says is that if you have terms that are separated by a plus or a minus, you can differentiate them independently and bring them back together again with that appropriate operator, that plus or the minus. So let's have a look. Let's have y equals 3x to the 5 minus sine of 4x, and then plus, what else should we include? E to the minus x. So this function now looks much more complicated than the two examples we've seen so far, and in fact it'd be perhaps quite difficult to picture what this would look like. Yet we can use our table to find the differential, and that of course will tell us the gradients anywhere whatsoever on that curve. So I want to find dy dx. Good news is my terms, first term, second term, third term, are separated by pluses or minuses, so I can do them individually. I can differentiate that and put my answer here. So again, I would have to go to my table and spot that it looks a lot like this, ax to the n. A would be my 3, and the n of course is the power, that would be 5. If I differentiate that, power comes down to the front and multiplies by a, and then I take 1 off the power. So a 5 comes down to the front, so I get 5 times 3, which would be 15, and I take 1 off the power. So 5 minus 1 would be 15x to the 4. I can now bring down this operator, so I can put my minus sign back in. And I want to differentiate sine of 4x. So again, I come across to my table and I see sine of ax. Well, in this case a would be a 4. So what do I get? I get 4 cosine of 4x. So I get 4 cosine 4x. I find my next operator, so I can bring that down as well. It's a plus. And I have to differentiate e to the minus x to finish this off. So again, I look here and I see e to the ax gives me a e to the ax. So a is just the coefficient of the x. It's how many x's I've got. How many x's have we got in this example? Well, minus 1. So my a is going to be a minus 1. So I have my plus from here. I bring down my minus 1. And then I have e to the ax, which in this case is just e to the minus x. And I finished. I've done all the differentiation. A little bit of tidying up to do. I have a plus minus 1, which of course would just become a minus 1. Typically we wouldn't even bother with the 1. We would have minus e to the minus x. So if I sort of cheat, I can now say that's just minus e to the minus x. And here we have the differential of this function here, this curve here. Okay.